for so, uh, a few words about the very common with so in the setup, I will be a bit, for simplicity, I will put myself in the geometric setting, although maybe everything I will say should also work when you work by QP instead of CP. Let's say C is where QP is an algebraic slow complete extension. And we're going to bring up integers OC and then what was done in the first paper was by Platten and Kimura. Then we constructed the following. So X of a ring of integers was maybe a property in Scholze key. Associated to this, what one now calls prismatic cohomology. So what kind of object is this? So this is an object in the dark category of change model. Complex projective module, so perfect object, where A as usual is content frame. So just vector and it also comes with the cryptos of convenience. So by then morphism after inverting. On the side will be the P minus. And right, so I always like to draw this picture of the Helix spectrum of AINF having two coordinates. One is some variable P, one is a variable and in this picture there's phi equals to 0, where P equals to P flat, so it's diagonal. And then plate of this under Venus, so you can phi is 0. So they all meet in the origin. And then there are some comparison isomorphisms, and in particular, if you specialize to this locus here, this gives you triple cohomology. Here you get the round cohomology, here you get basically hot state cohomology. If you specialize here to here you get it cohomology for generic fiber. So so maybe two things that I want to state here is that if you take that and you base change to the bit vector plus the residue field, this is actually the crystalline cohomology of special fiber. So this is something that, so this locus, this crystalline locus, is definitely something that knows about special fiber somehow. But if you take the prismatic cohomology and somehow restrict it to So you can draw this as some kind of vector bundle on the spectrum system if you want. And then if you remove this locus, you look at this part here, this whole part. This is often called y 0 infinity. Spectrum of the from which we removed the fifth one. This depends only on the generic fiber. And for example, like the third one, the negative perspective, if one takes this prismatic cohomology and tends it from a in one of the mu, for a mu certain element from -1, where epsilon. So the vanishing looks at mu, the grid line locus, but then also maybe this round locus, maybe depending on how I normalize things, also the Hodge locus on the necessary. Then actually this canonically anthropomorphic to the Park homology of the generic fiber. These two cases are not quite the same. Sometimes this is binary in some ways because it says it's enough to algebraically invert mu, whereas here we use kind of analytic localization. On the other hand, this keeps track of, say, the ground point through while and so there's another question that I'm not sure. Can one define cohomology of rigid spaces? Taking values in some kind of polycurrent fuse on the y0 chain. But then, I mean, it's got the proper smooth case about where cohomology is finite. But if you remove the property assumption already, then for like affine smooth over scheme, prismatic cohomology is interdimensional. So you can only expect to get some kind of polycurrency. And somehow comparing well with prismatic cohomology of quantum models. Okay, so here's the kind of question I want to say a few words about in this talk. But there is an important warning I have to make before we get started. So the best possible scenario can work. What would be the best possible scenario? The best possible scenario would be that you have some kind of formal scheme, random scheme. Then you have the rigid Right, fiber. And then you should have some prismatic cohomology here that goes to some kind of colored modules on alien. Then you would like to maybe have some function here that goes to solid module on y0 and n. And here you can also take the generic fiber. And so you would like such a diagram to be. This is possible. And the reason is quite simple. You can just start with the formal scheme X, which is this of OC mod P to the n. So this maps the rigid fiber of this that is just empty. So this should definitely then go to 0. But it's a prismatic cohomology of this is what's known as a prism of OC mod P to the n. It is some algebra you can write down more explicitly. So you start with AN, and then you join what do you have to join? You have to join P to the n over Delta ring is then complete. Right? And so this goes somewhat to the base change of this algebra from AN to the structure sheet of y0 infinity. But this is actually, this localization is non-zero. So, I mean, already if n is equal to 1, n is equal to 1, then the prism of OC mod P is better known under the name of A Cris. And A Cris in this picture is really some region, again, depending on my normalization. I'm not quite sure which point it includes, but definitely the crystalline point, definitely the round point, it somehow spreads out to this region and intersects not trivially. Intersects not trivially with this region you're interested in. So this cannot possibly work. And so as you increase n, actually you will get larger and larger regions of this picture. So if n is equal to 2, you would get larger regions here, although you would take away from the Hausdorff, but then this Frobenius inverse translates. All right. But one way to, and so starting from here, there are several ways to weaken what one wants. One is to somehow replace y0 infinity by a smaller space that's precisely singled out by the requirement that these things actually get filled. And I expect that there is some kind of theory that works in this case. But I want to talk about a different theory where when someone takes some kind of perfection step, because this is a theory that's very much related to this hot state effect that some people here are thinking about. comment on this in just a second. Okay, so two possible ways around. One is to replace wider infinity by a subspace. I'll fill that. What remains after you've done this is some kind of over-converging neighborhood of the following union or set of like psi inverse of. Let me call this on state point phi. So state point phi inverse of your state point multiplied to minus n of your state point. And so these phi minus n of the state point in the picture, they converge to the power point. And well, such an overconverging neighborhood maybe doesn't make much sense as a rigid space. But it does make sense with, at least, for example, within the framework of analytic geometry that I've been developing with stuff out. And I expect that with this variant, there should be some kind of way of making such a diagram. But I want to talk about something else today. Second is to pass to now it's to take uncompleted. Critical for talk about it. So, namely, if I take the colimit, and really the uncompleted colimit over the Frobenius of the prism of Hausdorff again, then all these tensor products. The solid tensor product uses colimits. Basically, the point is that it takes that for zero infinity it's zero. It's enough to show that for all 0, n, it becomes 0. But then the Frobenius twist is somewhat the same thing as instead someone trying to base change to e to the minus Rn, and then take colimit over R. But then this is localizing around base changing this prism of Hausdorff p to the n is just somewhere here, and maybe it has some kind of poles at the points. But then you're base changing to a region that's here, and this is 0.
You don't need these to be the same ends, do you?
I don't mean these to be. But keep in mind that's not all. Yeah, so for any given n, and for any given radius r, you can find some sufficiently high power of Frobenius, maybe to call it n, so that this y0 e to the minus mr and this prism of Hausdorff p to the n, that they somehow trivial intersection. Okay. So this is a justification that the following theorem is sensible. So it's got with x, which is let's say it would work for much more general formal schemes, but let's say for this talk it's some of the kind of formal schemes from the theory of rigid spaces, so these different formal schemes, so a couple of cheap kind of type and so on. And you know, the following construction. We first take a systematization of X, which is some kind of formal spec. So this was done by Grinfeld and now I talk to this world of analytic spaces in the sense of Feldman level. Which has the advantage that, first of all, in this world, we can talk to the generic fiber, but also in this world, we can take uncompleted colimits on the level of algebras, and so the limit on the level of spaces here corresponds to an uncompleted colimit on the level of rings. And so this fiber product, if I some base change from A in to this modular infinity, and then it's more. This functor inverts admissible blowups, and hence induces a function of the generic fiber. That will be noted by taking a rigid place to perfect methodology. All right. Yeah, so some explanation. First of all, I mean, this, let me state some kind of low-level translation or full information, but the consequence is that on the level of cohomology, it means that if you take this cohomology or continuous cohomology, base change from A into modular infinity, then this inverts this one. And this column is really, again, non-complete. Yeah, which is kind of in particular includes this thing. Right. Okay, so some explanations. The X present in the form of that. And there are several ways to describe it. So one way to think about this is this filter, some kind of cover. Then so you get this diagram that you cover X as in terms of integral. Where this guy here is the factoid, and these are so-called semi-perfectoid guys. There's a lot of rings. These are quotients of perfectoids. Because then the product would be basically perfectoid, but then when you take the third product of X, you enforce an extreme relation. And then if line is any semi-perfectoid guy, then the prismatization of this is actually just the formal affine. It's actually just affine. Strip of something, and the strip of this is strip of some R. And this is a prism of R, we did. Usually it's like no derived issues, and it's just a universal prism subjecting into R. The initial object is depending on prism to R. And so then in general, we can write any X, I'll have a presentation in terms of the prismatizations of like a perfectoid cover. And presentations of all this cover. You can also write down the functor points of X prism. For R in the inf algebra, say that the unvalued point of X prism of R, and this should be equal. Now the following, you take point of X, coefficients in the big vectors of R mod some element psi, where what does psi mean? Well, A-inf maps can only be to the big vectors of A-inf because A-inf is a delta ring. So this gives you something like and this goes further here. And so psi is an element in here, and then wire each canonical on that side are regarded as an element in the vector of R. And then All right, so let me say just a few words about these analytic spaces that we're using. So we start with the category of analytic rings. That's well that I defined. So these are pairs A, where A is a condensed ring. And M is a certain extra data, which I mean there are several different equivalent definitions of what an analytic ring is. It's always a pair of such a condensed ring and some extra data. And what precisely this extra data is depends on your different people have different favorite choice for this. But what it's meant to do is it's supposed to single out the class of complete A modules. And actually, the category of Hoover pairs puts fully faithfully into these things, sending any pair AA plus to something we call AA plus solid. And this is actually the underlying condensed string of this is just the one corresponding to the topological algebra that's part of the Hoover ring. The Hoover ring, there's this funny extra data of the ring of integral elements that Hoover always has. And it turns out that there is a precise way of taking exactly such a choice of integral elements and using it to single out a class of complete A modules. Quite it's a series fit well. And so then we have a functor from which one might call the F analytic spaces. To metric model indicators, which takes any such pair A, M and sends it to the right category of complete A modules. Module. And from this data model, can introduce a certain growth topology on here. How do we term the topology? So basically, it's more or less the universal defined growth topology with respect to D satisfies consent. It's slightly more subtle than that, but that's the idea. So it's closely related to the notion of descendable maps.
before you raise the corollary, so, how come the analytic, where did the analytic structure go? Like, from this patent here, the corollary.
Where did the analytics? Sorry, what?
The theorem was about like the analytification, some kind of.
Yeah, but I mean, like, yeah. So I mean, I'm just taking the cohomology and some under the notification. So basically, what I will do when I analytify is I will just, I mean, these things are just affine guide, and I will just send it to a similar affine analytic space, and the cohomology will not change.
Okay.
But then, okay, so then I was also taking a fiber product. That's a fiber product in the analytic space, but of course, just a tensor product in the rings. And so then we take some kind of maximalist approach to our definition of analytic spaces. So the definition will just be that the analytic space really, maybe one should call these stack from the start. But is achieve once go. And then by some abstract six functor nonsense, so actually, the affine analytic spaces. Yeah, you have the category of analytic spaces. This includes the affine ones for efficiency, and they generate everything under colimits. And then abstract six functor. Right. So here we have this functor. D is the matrix model and then category. Kind of extended neatly to here. Back to some natural conditions like this, actually the conic extension is map. They extend neatly to here, which includes means that you have some kind of tensor and fallback functorialities. So for any x, you can have some derived category of quasi-coherent sheaves on this. And you can pull quasi-coherent sheaves back and you can tensor them. But also, you get a lot of street maps. Tensor. Pullback. X, Y. Okay. But also, for many NF-low from before, satisfying all the expected things, projection formula, proper base changes. Yeah. And this funny world of analytic spaces really includes, I don't know, usual analytic spaces can be embedded into this world, complex analytic spaces can be embedded into this world, and so on and so forth. Okay. Right, and so like if X is some split R, then X analytification will somehow be, well, let me, the F analytic guide, focus function unspec. Unspec of, I guess, the R. And so then also if I have prismatization of X, I'm going to try as a presentation again. Thank you. I'm going to cover in terms of the identifications of all these guys, which are affine. So this explains how I pass through the world of analytics. Okay. And I guess implicit here is that I need to show that it's independent of kind of the presentation I chose, and this actually involves a little bit of checking. In particular, needs that the code topology is fine enough. That's kind of getting faithfully that covers that are implicit in this kind of formal stack here, this kind of FTQC stack, that they're still covered when I pass through the conjunction. All right. Okay. All right, so let's remind you of the theorem, and I'll get to proof and hopefully have time for a few comments about it. The theorem was that sending any homoscheme X to the following construction using the homogeneous of X prism multiplied times over and this inverts let me give a check of the proof. Okay, so we just need to check something, namely that is if X prime X is an admissible law. So we need to show that this function that I will now call F one. And now it's really true that if I look at the prismatization of X, that is prime prismatization of X, then that this is actually descendable map. Which implies that also, because descendable maps are bounded index are stable under some kind of full limits and also on their base change, it also means that if I apply this functor f, and this is still descendable. So it's some kind of surjective map in this world of sheaves. So it suffices to prove that after fullback f of x prime. So it suffices that f of x prime times f of x. F of x prime. Fine. But also prismatization and commutes with limits. And also the other operations there with all limits. So this is actually just f of the product.
But the stability is the complete sense.
Yes. Right. But this means that instead of proving that it's the projection to one factor here, we can also instead prove the diagonal. The diagonal from x prime prime uses right, so after all this, after this kind of preliminary reduction, we can assume that the dot of generality, this map from x prime to x, is actually close to max. But then, because everything is kind of local, we can also x and then also x prime. We can think that. But now, how did we actually define this prismatization? We use these perfective presentations. So these perfective presentations. To reduce to the case where these are actually semi-perfectorized. The x and then also x1.
How can the admissible blow up be a closed immersion?
Yeah, so something also needs to prove that if I have a closed immersion which only kills p torsion element, then this induces a nice Morrison of the generic type. And so then the key case is the following. X is something like this of OC, and then we're in a semi-perfective situation, so with a variable we should join all the C-bar roots. And then we have something where we can only model it out by px. And then inside there, we have x prime, which is the one where we realize that along the generic fiber, x is actually equal to 0. So we could also model out by x and not change the generic fiber. And then you just need to show, so in this case, the prismatization is just something affine. So the computation you need to do is really just one operation. These are thin perfector length, like regular thin perfector, so the corresponding prismatic cohomology is really just one ring. If I write down, that would be perfect. With that becomes an isomorphism. After taking the colimit over unit of blank and place changing from A in to the point. But what are we saying? So if I take just the prism of this one, I would get, that's a perfectoid situation, so I just get A interjoin X in all T4 roots. And then if I model by Px, this means I should adjoin divided powers, or what, because in this case, the amount of the same thing is to adjoin Q divided power. All n I adjoin this element again. And so the description here is very similar. So if I join these things, then I've definitely also joined these things, so that definitely this map. But on the other hand, like once I apply Frobenius, then actually you can also show actually one copy of Frobenius is enough to somehow basically do the computation. If you base change the config variables R here, then sometimes power of Frobenius is enough to get a map in this direction. Basically, because this element P flat somehow becomes invertible once you pass through the element, once pass through the ring, and actually when you pick radius, you can really bound it and then so move these powers and hear them as a denominator. So, and then, I mean, yes, that's basically what you have to do, right? Because the only thing that can really happen when you have such a close convergence to like more generic fiber is that you had some elements which were where you just kill p times some equation, and you want to do more. Once you have that case, and you know that everything behaves well on the fiber products, you can really conclude.
The question, like with regards, it's clear notion for like derived formal schemes.
Yeah, yes. Maybe my formal schemes are all to be derived right now. All right. So, how much time do I have left? Okay. So, let me try to say a few words about the geometry of the data, which we need to stack over the quadrant. And one thing is that phi here is really an automorphism. So if you want, you can also like remove 0 here and then descend just to the top potentials. So there are like several interesting fibers. So one interesting fiber is the fiber over the shape point. There the conjecture, and I think it shouldn't be hard to prove, is that if you take this Um, and base changes. Okay. Then this is the analytic hot stake stack. That's at least implicit in the work of functions. And I would get some model like also and so particular when you specialize to this point, then this stack will actually live over X itself. And the map itself, it should be a germ banded by taking the tangent bundle of X, but then I'm not sure if you know this. Let me put a dagger here. It's like the intersection over all r bigger than 0 of like inside the tangent bundle, you can say fix some norm, and if you fix the norm, then you have all the balls of varying radius, and then you just pick like you have the 0 section inside your tangent bundle. Tangent bundle of X 0 section embedding, and then this tangent bundle dagger is just some kind of small neighborhood, like specified small radius around 0. By that. And it's a very non-trivial germ. It's some other germ which implicitly appears in the PD simple correspondence, which is what they're working about.
So I guess X is smooth.
Oh yeah, so X is smooth. Sorry, and this, but I should twist it by change this by 1. Okay, so I'm running out of time, so let me just talk one thing about different fiber over a different ensemble. The different really, not just convenience translate, but really different. So there the conjecture is that. So maybe I should make before it's not written. So you can take the diamond of X, and then sometimes you can take the curve y0 infinity for the diamond of X. Well, usually it's only defined for a perfectoid space, but again, you can present the diamond colimit of perfectoid spaces in the world of diamonds, and then take a similar colimit of these spaces in the world of analytic spaces. So this can actually be defined as an analytic space in the same category. And then there is actually a canonical map towards perfect prismatization. In some sense, this here is the completed perfection, this is the uncompleted perfection. They're supposed to be very close. And In particular, there's like a map from X diamond to X on state. Then the map I've described over there gives a map from X diamond to X on state, and something that's their work on the Felix correspondence about is a conjecture that these two things actually have the same perfect complex. So the perfect complexes here are related to V vector bundles or Poisson vector bundles. And they expect that all of them actually descend uniquely to the matrix. All right, and so so if I take a different myself, prime, then I somehow get a X diamond or X diamond and then realize again over C, but here I take X diamond and then realize somehow over C prime. Which you can also do. And then there's a map like so. And I conjecture that this induces an isomorphism in what one might call the RAM stack of the diamonds towards this guy. Where this is somewhat given by quotienting by the equivalence relation, which is some kind of overconvergent neighborhood of the diagonal. It can be defined even for diamonds. You can define such a RAM stack always. And basically, I'm conjecturing that the equivalence relation, so this is surjective, the equivalence relation that presents this thing as according to this one is precisely the kind of thickened diagonal. All right. I guess I'm over time already, so I can just. Thanks.
This doesn't quite recover the fact that the things of it only depends on the generic fiber when you restrict to the zero.
Right. So yeah, only after section. I mean, yeah. So one, like back to the original question. So we have this wide infinity here, and then there was a lag somewhere. And so one way to think about these things is that it's a vector bundle on this region, vector bundle on this region, and then modification, right? So that. And so basically, this theory is about this kind of region. You can make a similar theory actually for this kind of region. This was more or less, one version was done by Dr. Salvador and Alberto Bazzani. And actually, one way one could also phrase this is that you just take this y0 infinity by a diamond and then take its round stack. This is a stack which will somehow also be into the model and which captures what's happening over here. And then there is actually this also the perfect prismatization. Well, you can only have there. Well, so I think change. That will be a canonical map like so. And so, right, so you get one vector bundle from here, you can restrict it to this part, or it's only to this part of you, and then this map uses modification. So you can actually also capture the whole modification of vector bundles, well, in terms of two steps. One is let's say I described here, and the other is actually in some sense easier. Just on the problem.
By the way, where was this independence proved? Like, is it in the original BMS papers?
The independence, yes. So you can just, yeah, so some of the independence just comes from the fact that you can describe explicitly what all these Stuttgart with one like are. So all these vector bundles on here, this region which are like here. And they are given by just the Tar realization and the modification happening at this point. This is data we know how to recover from generic fibers. So you have the cohomology and you have to speak around plus that is here. But it's somehow only really, there you only really knew how to construct things here and here, and not really directly fill out the whole picture.
Yeah, so how much descent does this construction have in X?
I have quite a lot of descent.
What does that actually mean?
Well, it definitely has a tau descent, and also like generic fibers are something. You have something which has a form model, which is some kind of history filter, and it should also satisfy descent for that. So you also have some kind of process atomic descent. So this construction has quite a bit of descent in X. And also, yeah, here I only define like rich space of a C, but really it works basically for all analytic spaces.
Okay, so if you do this for analytic Alex spaces over DP, like, so does it have like greater descent? Can one extend this to diamonds, or like how can we get this idea? I don't know how quasi-atomic relates to.
I mean, diamonds. I mean, it's quite important to remember some kind of non-reduced structure here. Like if you would identify all the semi-perfector rings with second reduced blueprints, that would be bad, which you kind of do in diamonds. Because then you would.
Case, it's just why the old.
Yeah, in the perfector case, it is just the old part perfector.
So if you have quite a something.
Yeah, yeah. So if you would enforce some of that you can descend to perfectoid things, then you would just recover the old one. But it's really about kind of more refined information where you can see such funny things that people would do things in the bundle, which have quite a lot of information.